The sights of many nations are set on lunar colonization with a broader vision of interplanetary habitation. But before buildings can be built, someone's gotta dig. That's where Astroport Space Technologies and Venturi Astrolab come in. They recently completed a successful field demonstration of a lunar excavator integrated with a modular rover platform. During testing, the system moved 94 kilograms of regolith in just 3.5 minutes. A strong proof of concept for automated construction on the moon. The technology is designed to create centered surfaces, turning loose lunar dust into solid landing pads and roads. This is critical because spacecraft landings kick up sharp regolith particles that can damage equipment and create operational hazards. By building stable surfaces first, the companies aim to reduce risk for future missions. Their strategy follows the idea of ports before ships, meaning infrastructure must be established before large-scale exploration and commercial activity can expand. The modular rover platform allows tools like excavator to be swapped for different tasks, supporting long-term flexibility and mission assurance. And when engineers need assurance from their parts, they turn to Mouser Electronics. Schneider Electric Modicon M17X logic controllers provide an economical, scalable PLC solution for a wide variety of applications. Supporting flexible scheduling, occupancy sensing, and analog control, they are configured using EcoStruxure Machine Expert HVAC software compliant with IEC 61131-3. The M17X supports multiple industrial protocols including Modbus, BACnet, CAN, and Profibus, and features embedded WebVisu for remote monitoring. With flexible power options, expansion modules, and wide environmental tolerance, Schneider Electric Modicon M17X logic controllers are an excellent choice for HVAC, refrigeration, and pumping machines. Check them out today by visiting Mouser.com or by clicking the link below. Electromagnets are important because they power the actuators, relays, and motors that turn control signals into real motion. For more, we present David's Corner.
Thanks, Andy. Today I've got a science experiment to show you. It relates to automation because most things that move in automation, they move thanks to the idea of an electromagnet, which is created through an inductor, a coil of wire. Well, here we have a simple steel bolt from Home Depot, a coil of solid core wire wrapped around it, and a 9-volt battery. There's some alligator clips to allow us to connect to the 9-volt battery. And once we make those connections, we can use this bolt to pick up paper clips. These steel paper clips are picked up because the bolt is now an electromagnet. If I disconnect the battery and the current is no longer traveling through the coil, I can't pick up the paper clip anymore. We've turned off the electromagnet. Why is the electromagnet useful in automation? Well, we don't always want the motion to be happening. Like in a relay or a solenoid, we only want it to happen when the electricity is applied to the coil. So as soon as we switch on the contact, the PLC contact or the magnetic switch, now we can pick up the paper clips, or we can move the solenoid or plunger coil more realistically, but we can do so at exactly the time that we want. Downside is it consumes a lot of electricity to run through the wire, but it gives us a lot of control over the system thanks to this idea of electromagnets. And this is a simple enough project that you can try it at home if you've got these devices. Andy, back to you.
All right, it's time to adjust your knowledge gains in our Smart Bit quiz with our 3 control automation questions. The questions are scored using actuator output percentage, and today we'll be testing your knowledge on the control system that failed. Let's begin with our first question for 25%. A humanoid robot monitors the factory floor when alarms trigger. The controller reacts aggressively to noisy sensor readings. What should the engineer do? Is it A, add a low-pass filter, or B, increase derivative gain? And the answer is A, add a low-pass filter. A low-pass filter removes high-frequency sensor noise before it enters the control loop. Okay, let's move on to our next question worth 25%. After fixing the noise, the motor suddenly starts vibrating and oscillating after a tuning change. What should the engineer adjust? Is it A, lower derivative gain, or B, lower proportional gain? And the answer is B, lower proportional gain. Excessive proportional gain can cause instability and oscillation. Reducing it stabilizes the loop. Okay, let's move on to our final question worth 50%. The robot stabilizes the motor, but now the system responds too slowly to changes. What adjustment improves responsiveness? Is it A, increase controller bandwidth, or B, add more filtering? And the answer is A, increase controller bandwidth. Increasing bandwidth improves response speed. Adding filtering introduces additional delay. Want to try again? Just click the link on your screen and be sure to check out our other AE videos for the latest in control automation.